Alright, so for this problem we have a link BD which is made of brass with a cross-sectional area of 240 millimeters squared. We have a link CE which is made of aluminum and it has a cross-sectional area of 300 millimeters squared. We know that these two links support the rigid member ABC, and we are asked to determine the maximum force P that can be applied vertically at point A if the deflection of A is not to exceed 0.43 millimeters. So basically we're going to start off this problem by drawing the free body diagram. And I'm going to go ahead and set our coordinate axes, just the standard x to the right and y going up. And then I'm going to draw ABC right here, and then I'm going to draw all these forces that we have. So we have the force P going down vertically like that. We're going to have a force through this member BD. I'm going to call it FBD. And then we're also going to have a force here in the member CE going downwards as well. I'm going to call that FCE. So basically looking at this right here, this free body diagram, we have two unknown forces, and then basically we don't know P as well. So our best course of action here is going to be to take the sum of moments and basically come up with two different, a value for FBD and a value for FCE dependent on P. So we're going to solve for those in terms of P and see what we get. And we're just going to take the moment at this point, point B, and the moment at point C to get those two equations. So taking the moment at point B, let's do that one first. And I'm going to take the sum of moments about point B, which is set equal to 0. And basically for that, I'm going to go ahead and be converting these millimeters distances into meters as I do this problem. So we're going to have a 0.125 meter distance times P for that one. And then we're also going to have the FCE there as well. And that's going to be a negative moment for that one. Negative 0.225 meters times FCE. And solving for FCE based on this, we get that FCE is equal to 0.556 P. And now we're going to do the same thing, taking the moment about point C to solve for that other unknown force in terms of P. And so for this one, we have the force P and then the force FBD. So we have 0.35 times P. That's a positive moment for that. And then we have a negative moment for the other one, which is negative 0.225 times FBD. And then solving for the FBD here, we basically get that FBD is equal to 1.556 times P. And so now we can actually use these values and then eventually come and solve for P using these. What we're actually going to do next is we're going to solve for the deformation in member BD and then also member CE. And I'm going to start with BD first. I'm going to call it delta B, but really it's going through BD. And the formula to use for this is the force going through that member, so FBD times the length of that member, so LBD, and then over modulus of elasticity, which is actually given to us in the problem statement, times the cross-sectional area of that member. And basically we have all of these things already. We're just going to go ahead and plug in all our values here and then solve for this in terms of P. So we have the 1.556 P that we found before. And once again, I'm going to go ahead and convert everything into units of meters just so everything cancels nicely. We have 0.225 meters for that length. And on the bottom here we have, I'm going to go ahead and convert the modulus of elasticity into pascals or newtons over meters squared so that everything still cancels. And for this one it's going to be 105 times 10 to the 9th newtons over meters squared. And then lastly we have our cross-sectional area, which is also given to us, and I'm going to convert that to meters. That'll be 240 times 10 to the negative 6th meters squared. And so if we actually go ahead and solve this, we get 13.889 times 10 to the negative 9th times p. So we're once again going to solve in terms of p and then use that later on. Now for the next one, we're going to call it delta c. It's going through CE. And again, same formula, FCE, LCE over ECE, ACE. We're going to use that value that we found before for FCE. So we have 0.556p, 0.150 meters. Then on the bottom we have 72 times 10 to the 9th pascals or newtons over meters squared. And then cross-sectional area we have 300 times 10 to the negative 6th meter squared. Now solving for that in terms of p, we're going to get 3.8581 times 10 to the negative 9th times p. So basically we have both of these deformation values in terms of p. And now what we're going to do is going up and looking at the actual figure, we're going to create a deformation diagram basically. So to do that, we're going to look at how this is going to change as this force P is applied. And so as this force P is applied, the length of member BD is going to increase and then downward in this sort of way, same direction that the force P is being applied. And the length of member CE is also going to increase, but it's going to increase upwards. And so I'm going to draw a deformation diagram so that you can kind of see what that looks like. So this horizontal line here is ABC, and then this is going to be kind of what the deformation will look like here. And so at each of these points, so we have the deformation of B, deformation of A, and then lastly over here we have the deformation of C. And then we have an angle theta that is caused by this deformation. And so this is way exaggerated. Obviously this is going to be a very small amount. And so something that can actually be used here, so we're looking for, let me go back up to the problem statement. We're looking for the maximum force P that can be applied vertically at point A. And so basically what we're going to want to find is the deformation of A, using the deformation of B and deformation of C that we found. And there's actually a way that we can relate these. So looking at this left triangle here, we have the deformation of B. So the deformation of A is basically the deformation of B plus this little extra amount here, which I'm just going to call delta prime. And these are similar triangles, of course, so this angle theta is also applied here as well. So that's also theta. And basically, since this is a tiny triangle with very little deformation, we can use a small angle approximation theorem. And what that states is basically the tangent of a small angle theta is approximately just equal to that angle theta. And we can use that in the case of this small triangle here to relate this side length here, the adjacent side length and the opposite side length. And this adjacent side length, of course, is LAB, which we are given above in the problem statement shown in the figure. So we can actually relate these angles and side lengths there. So the angle theta, which is approximately tangent theta, which is equal to the opposite side over the adjacent side. So that's delta prime over LAB. And we're actually going to be looking for this delta prime, and we can just add the delta prime to the delta B to get delta A. And so basically this just becomes delta prime equals theta times LAB. And so now basically what we need to do with this is we need to actually go ahead and find what our theta value is. And so one thing that we can do here is we can actually make a change to this deformation diagram. So I'm going to go ahead and do that now. And what I'm going to do is I'm going to shift this line here down by delta C so that we have a perfect triangle here. And this is kind of what that's going to look like. And basically we're adding delta C at every point to shift it downwards. So this here is going to be delta B plus delta C, and then this here is delta A plus delta C. And then we know that this is LAB and this is LBC. And then again, this is still theta. And so what we can actually do is we can find theta based on delta B plus delta C and LBC. And so again, since this is a small angle, we can use a small angle approximation again. And theta in this case is just equal to delta B plus delta C over LBC from that small angle approximation theorem. And then I'm going to scroll down a little. We're basically going to plug in the stuff that we got before. So our delta B is going to be 13.889 times 10 to the 9th times P. Our delta C is going to be 3.8581 times 10 to the negative 9th times P. And then all that is going to be over our LBC, which is 0.225 meters. And our theta then just becomes 78.876 times 10 to the negative 9th times P. And so now we can actually use our small angle approximation that we got here to find our delta prime value. And so in this case, our delta prime value is going to be our theta times LAB. So 78.876 times 10 to the negative 9th P. And then our LAB, let me go back up and see what that was. It was 0.125 meters. And so basically we get that our delta prime is equal to 9.8595 times 10 to the negative 9th times P. And so now we actually want to find our delta A. And in this case, like we discussed before, delta A is equal to delta B plus delta prime. And so we already know the value of both of these, and we can just simply add them. So our delta B, 13.889 times 10 to the negative 9th times P. Our delta prime, 9.8595 times 10 to the negative 9th times P. And when we add these up, we get that that is equal to 23.748 times 10 to the negative 9th times P. And now we actually know what this deformation cannot exceed. They gave that to us in the problem statement. We know that delta A cannot exceed 0.43 millimeters. And I'm going to go ahead and convert that into meters and then basically just solve for P. So our delta A, and that's from the problem statement, 0.43 times 10 to the negative 3 meters. Set that equal to what we found just above, 23.748 times 10 to the negative 9th times P. And basically our P value solving this becomes 18.11 kilonewtons. And that's it for this problem.